we are ready. Okay, so make sure, so, hopefully it's talking about that one. Let me just make sure I'm not on mute. Okay, good. All right, so who's on here anyways? Heather, Kobe and Kobe, cool. All right, so just as a reminder, I think I saw your guys' submissions, but just as a reminder, submit bonus assignment to Gradescope. I think I made it due, I think it's due tomorrow, due April 1st. I'm gonna put question mark here. Let me just see if I can check it on my other screen here. Gradescope. April 1st, yeah. Okay. So looks like it's due April 1st at 11 p.m. But maybe check that at 11 o'clock, just because I don't know if it's adjusting for my time zone or not, because I'm out in Ottawa right now, and so I honestly don't know if it's adjusting for that or not. Some apps are and some apps are not. Oh well. So put a little question mark there at 11. So not at midnight, at 11 p.m. Okay. So I saw your guys' submission, so hopefully it went well. I know some people are having trouble logging in, but obviously that's not the case for you guys, but let me know if that's a problem. And also, I think you guys are all good, but for anyone who's listening later, if you don't have, if you haven't had access to WebAssign this whole term, then please just get in touch with me and we can figure something out. All right, so I almost wrote example, but let's do review by way of example. So last day we were talking about how derivatives affect the graph of a function. And so if we have something like f of x is 2x to the 3 minus 9x squared plus 12x minus 3, we can find things like find the intervals of increase and decrease. Intervals, of increase and decrease. Oh. Yeah. The local max and min, so the local maxima and minima. Maxima and minima. We can find intervals of concavity. Intervals of concavity. And we can also find inflection points. Inflection points. Now the first two, right? The first two are using the first derivative typically, and then the last two are using the second derivative. So we'll get started here. We rely on critical numbers, right, for the intervals of increase and decrease, right? And so we have to find critical numbers So for the derivative of f, if f of x is this polynomial, right, the derivative is nice and easy. We get 6x squared minus 18x plus 12 is the derivative. So then the type 1 critical number, that's where the derivative of f of x equals 0. And so we set 0 equals 6x squared minus 18x plus 12. What I see is I see a common 6 that I can pull out. So I'm going to pull out that common 6 and get 6 times x squared minus 3x plus 2. That's going to make it easier to factor, right? So I've got 6 times x minus 1 times x minus 2. So here, x equals 1 and x equals 2 are critical numbers. Critical numbers. Remember, type 2 critical numbers are when f prime of x does not exist. In this case, we're not dividing, we're not taking the square root, there are no logs. And so type 2 critical numbers are not applicable for this function, right? So, but we do have critical numbers. We have x equals 1 is a critical number and x equals 2 is a critical number, right? And so at these points, x equals 1 and x equals 2, things are going to change. It's either going to be a switch from kind of, if you've got an x to the 3 function, then it's going to be a switch like this here. That could be a critical number, or like this, right? Or if you've got a minimum, then that's a critical number, right? So all those would be critical numbers. So we're just going to try to figure out which ones apply here. So I think the easiest way to do that is to just use a number line. And so I'll use a new page here. I've got critical numbers at x equals 1 and x equals 2. How it behaves beyond that, it'll all be the same, right? So what I do is I just pick values in each of these intervals, let's say 0, 1.5, and 3. You can pick any number in this interval, any number in this interval, and any number in this interval, right? So I'm just using these as just a guide, right? And so what we do is we evaluate the derivative of f, which we just decided was 6 times x minus 1 times x minus 2. If x is 0, then I get 6 times a negative number, right? We're only concerned about the sign here. We're not going to spend any time evaluating at these values, right? We just use 0 in here as a quick judge to make sure it's positive or negative, or to check if it's positive or negative. 0 minus 2 is also negative. So overall, I get a positive times a negative makes a positive value, which means that f of x is increasing, right? So here, right, in the next interval, right, between 1 and 2, then we've got 6 times, let's use 1.5 as a judge. 1.5 minus 1 is a positive number. 1.5 minus 2 is a negative number. So overall, I've got a negative number, which means f of x, the graph of f of x, is now decreasing, right? Because my slope is negative. Moving over to anything greater than 2, well, I've got 6 times 3 minus 1 is positive. 3 minus 2 is also positive. So I get a positive number, making it increasing here. Right, so we know that based off of the derivative, right, that's the slope of the tangent line. So if I've got a positive slope, and then at this critical number x equals 1, it switches to a negative slope, that means this must be a maximum. And then from between 1 and 2, we've got a negative slope. And then at 2, it switches to a positive slope. So it looks like we've got a maximum and then a minimum, or a local maximum and a local minimum that we're dealing with here. So this is what we call the first derivative test. Which is what we did above. Says that at x equals 1, we've got a local max at f of 1 equals 2, right? F of x was 2x to the 3 minus 9x squared plus 12x minus 3. So if we plug in x equals 1 here, let me just copy so I don't have to write that all down again. All right, I'll put it here and shrink it way down, just as a little reminder. So f of 1 is 2, so we've got a maximum at y equals 2, or f of x equals 2, and then at x equals 2, we said we have a local minimum at f of 2, which is 1, right? Plugging in 2 into each of these x's. So as far as what we were going to do here, right, we were going to find the intervals of increase and decrease. We already found the local of maxima and minima, so we actually did this first. So let's now find the intervals of increase and decrease. We actually already did, right? Increasing, decreasing, increasing, but we didn't write it out. So let's write it out. So it's increasing on the interval from negative infinity, right? This is negative infinity, this is positive infinity. So from negative infinity up to 1, not including 1, increasing on negative infinity to 1, and then it's decreasing and then picking right back up at 2 and onwards, it's increasing again. So union 2 to infinity. And it's decreasing, oops, on interval 1 to 2. Not inclusive because those are our critical points, right? And so the derivative there is 0, which is how we found those critical values. So it's not including those points. We can use the second derivative. Use the second derivative to find, let's see here, the second two things, the intervals of concavity and the inflection point. So potentially. To find the intervals of concavity and potentially the inflection points. So the second derivative, f double prime of x, well, the derivative of f was 6, actually it might be easier to just use the polynomial version. 6x squared minus 18x plus 12 puts me at 12x minus 18 for the second derivative. So I get 12x minus 18 for the second derivative. So I can pull out a common 6. Is what I'm seeing. 6 times 2x minus 3. Just using the same method. You don't have to pull out the common factor, but it just makes it easier because we're going to find where this thing equals 0. And so 0, 0, 0 equals, actually, you know what, to make it cleaner, you know what I'm going to do? I'm going to set this equal to 0 on this side, because when I put it underneath the f double prime, it just looks like, I don't know, it looks crowded. It looks like this double prime switched to 0, but actually we're finding the second derivative, figuring out what it is, and then setting it to 0. So maybe just to make it look nicer, I'll do that. I can divide both sides by 6, so then I get 2x minus 3 equals 0. Now solving for x, I get 2x equals 3. So x must be 3 over 2, or if we prefer, 1.5. Same idea, right? This would be, you don't want to call it a critical value because it's from the second derivative, but it could be a potential inflection point, right? There's only one, but this is where we switch from concave up or down to another type of concavity. So we can break up our number line again. Now we've only got this 1.5, and negative infinity to positive infinity. And I'm just going to pick 2 points on here. 0 and 2 sound good. Just something easy to deal with. F double prime of x, we decided was 6 times 2x minus 3. 6 times 2x minus 3, which is 6 times 0 minus 3, or in this case, right, still again, I guess I'm just interested in the sign. So a negative number, 0 minus 3 is negative, so I get a negative number overall. This tells me that f of x is concave down. Concave down if f double prime of x is less than 0, right? So if it's negative. Let's have a look at the second derivative when x is 2, for example, right? So on the right-hand side of 1.5, we get 6 times and then 2 minus 3. 2 times 2 minus 3. So 4 minus 3 is positive. So I get a positive number. So f of x must be concave up. Right, and up if f double prime of x is greater than 0. So we wanted to find the intervals of concavity. So here we can say that it's concave up on the interval from negative infinity to 1.5. Oh, that's concave down. Concave up from 1.5 to infinity. 1.5 to infinity, and concave down, that's from negative infinity to 1.5. If we're switching, right, so at 1.5, right, it goes from concave down to concave up. So at this point, 1.5, right, this is an inflection point. It's an inflection point when it switches from being concave down to concave up, or vice versa. Right? If we were going concave up to concave down, right? Either way, that's an inflection point. So we have an inflection point at x equals 1.5. Okay, we answered all the questions, right? We found the intervals of increase and decrease, we found the local maxima and minima, we found the intervals of concavity, and we found the inflection points. We can sketch this all out just to get an idea of what this thing looks like, right? We can put all these things together, and so we can sketch f of x equals 2x to the 3 minus 9x squared minus 12x, minus 3. And it's going to look something, probably not that great of a graph, but here we go. Something, let's see here. I know I've got critical values at 1 and 2 and an inflection point at 1.5. So what if I do 1 and 2 and here's 1.5? We decided that when x was 1, we had a maximum, and the maximum value was at 2. So here at 1, 2, we've got a maximum. And then when it was at 2, when x was 2, y was 1. So here we're at 2, 1. That was a minimum. If we plug in x equals 0, we can find where this thing, we can easily find the y-intercept, right? 0, 0, 0. So the y-intercept must be at 0, -3. And so kind of way down here, not really to scale anymore, is it? But I've got a page break right here. So kind of scooching it. So then at 1.5, I know I've got an inflection point. I know I'm going to go from concave down to concave up, which makes sense if I'm going from a maximum to a minimum, right? And so what I can do is I can sketch this thing. Of course, it keeps going here, but and we could spend time figuring out the x-intercept as well, but let's not worry about that. Oops, went down further than the minimum. Oops. There and there. Nice. So it looks something like that. All right, I'm gonna check for if there are any questions here. I don't see any. Right. So that was section 4.3. So today we're going to do section 4.4 and get into 4.7, which is very exciting because it's actually our last section because we're cutting 4.5. And so today we're doing section 4.4 and 4.7, probably just starting it. We're not doing 4.5 this term, which is great because it's sketching. So we don't have to worry about that. Things like what we just did here, right? That would have been a preview for section 4.5. We're not doing that though, so yay. And section 4.7 is our last section, which is actually kind of a fun section because it's on optimization. So we've just got section 4.4 and 4.7. And then what we've decided to do, because we're not doing the sketching, we're going to include 4.7 on test 4. So I should put that in. Section 4.7 will now be included on test number 4. Since we are not doing 4.5. Oops, 4.5. And test number 4 is on Tuesday. All right. So we want to be ready for test 4. So next day, what I'll do as per usual is I'll give you a breakdown of what to expect for the test after we finish section 4.5. And then we've got the test 4 on Tuesday. This is the reason you have to figure out how to upload on Gradescope, right? Because you're going to do your work at home, of course, and then you're going to upload your work kind of within a time frame, the class time, of course, and then that's how you're going to submit it, right? So you want to make sure that your Gradescope is up and running. You don't want to be dealing with that when you're trying to submit your test. So I guess I should check for questions here. Oh. Any questions about all that before we start? Okay. So section 4.4 is going to be a throwback to limits, but it's kind of a fun shortcut to some limits. indeterminate forms, indeterminate, yep, forms, and L'Hopital's rule you might also see it spelled as or L'Hopital's rule. Kind of a fun fact. So L'Hopital himself spelled it with the S, but then kind of spelling evolved, and so now you would probably write L'Hopital's this way. It really doesn't matter which way you use. It's just kind of a fun thing. So you can use either or. So we're talking about limits, so kind of a throwback to limits. And so recall some limits from chapter 2 kind of looked like, as a quick example, if we want to find the limit as x approaches 1 of 2x minus 2 over x squared minus 1, right? If I plug in x equals 1 in here, right, we can try that first. It looks like I'm going to have 2 minus 2 over 1 minus 1, that's 0 over 0, which we know we can't do, right? We can't divide by 0. And so this looks like looks like 0 over 0. And just as a heads up, this is one of the indeterminate forms that we're going to be able to deal with L'Hopital's rule. So in chapter 2, though, we figured out, we had some methods of dealing with this. So we said, okay, well, I'm going to rewrite this. I'm going to factor out a common 2 in the numerator and say 2 times x minus 1. And then I'm going to factor the denominator as x minus 1 times x plus 1. Oops, plus 1. This x minus 1 can cancel with this x minus 1, and so then I'm left with the limit as x approaches 1 of 2 over x plus 1, which we would just put as 2 over 2, which is 1. So the limit exists, right? And so here, right, these are the methods that we developed in chapter 2. What we're introducing here is if we have something that looks like this, 0 over 0, and I'll show you another example that also works, then we can use L'Hopital's rule. So another example, if we have the limit, so an infinite limit as x goes to infinity of x squared minus 2 over 2x to the 3 plus 4, this, if we look at it, right, we've got x squared, x is going to infinity, so this is going to infinity. This is also going to infinity, right? And so we've got infinity over infinity. looks like infinity over infinity, right? So what we had to do to deal with this was, okay, well, the one trick that we had was dividing everything by the highest power in the denominator. So we can do that here just to see. So the limit as x goes to infinity of x squared minus 2 over x to the 3 over 2x to the 3 plus 4 over x to the 3. Right? Just using that trick that we learned in chapter 2. It was a long time ago, I know, but we'll have to dust them off. The limit as x goes to infinity of x squared over x to the 3 minus 2 over x to the 3 over 2x to the 3 over x to the 3 plus 4 over x to the 3. Okay, if we simplify this, I get the limit as x goes to infinity of 1 over x minus still 2 over x to the 3 over 2 plus 4 over x to the 3. Remembering that as x goes to infinity, 1 over x or 1 over x to the 3 or any sort of 1 over x to with x to any power is going to go to 0. Right? So then we get 0 minus 0 over 2 plus 0. That's going to be 0 over 2. Oops. 0 over 2, which is 0. So the limit exists. Right. So what we're going to say, right, is we've seen 0 over 0 and infinity over infinity. These are called indeterminate forms. So 0 over 0 and infinity over infinity are called indeterminate forms. So in comes L'Hopital's rule. L'Hopital's rule says that if we have a limit, so suppose we have a limit of the form, the limit as x approaches any a, and a can be infinity, of f of x over g of x. Okay, so just any limit where we've got a fraction. A trick later that we'll use is to rewrite our limit as a fraction, but we'll get there. Such that the first condition is that the limit is indeterminate. The limit is indeterminate of the form 0 over 0 or infinity over infinity. And so that's going to be very important, right? So here, how can I? That's going to be important. Otherwise, it will work, but it's only guaranteed to work if you've got this indeterminate form. So, and of course, f and g, well, not of course to you yet, but f and g are differentiable at x equals a. And the third and final condition is that g prime of x does not equal 0 near a. Okay. Then what we'll say is that the limit as x goes to a of f of x over g of x, right? So that's the limit that we started with here, can be rewritten as the limit as x goes to a of f prime of x over g prime of x, right? That's going to be huge if this limit is a lot easier to deal with, right? Notice that this stays the same, the limit as x approaches a, but what we're able to do is we're able to rewrite, if this thing is hard to find the limit of, then maybe the derivative of the top over the derivative of the bottom. Notice that you're not taking the overall derivative, right? You're just taking the derivative of each of them individually. So that's going to be huge if we can find these derivatives and they're easy to find the limit of. So assuming the limit exists. So I'll put a box around this. That's what this whole section is about, L'Hopital's rule and how to use it. But what you'll find is that it's going to make your life a lot easier when you're dealing with limits, right? When you go back and work on limits, having L'Hopital's rule is going to be make things a lot easier. So one note, right? Or I'll say notice that the limit as x approaches a of f prime of x over g prime of x, these are the individual limits. Individual limits, right? Not the quotient rule. Right, that's going to be important. You just take the derivative of the top and then the derivative of the bottom, and then you smush them back together. So for example, we'll do a ton of examples here. The limit as x approaches 1 of the natural log of x over x minus 1. Well, if I plug in x equals 1 here, the log of 1 is 0, and then 1 minus 1 is 0. So here I've got something of the form 0 over 0. So this is, so I can use L'Hopital's rule. So what I'm going to do is I'll say here, L'Hopital's rule says that I can rewrite the limit as x approaches 1. Oh, I guess I can clean up that limit. The limit as x approaches 1 of the derivative of the top, the derivative of log of x, or the natural log of x, is 1 over x, over the derivative of x minus 1 is just 1. So then I have the limit as x approaches 1 of 1 over x, which is just 1 over 1. So I get 1. It's going to be a lot easier than trying to rewrite this and factor it out, because here I already know that the limit should be 1. I'm not sure how I would rewrite this, right, easily to try to figure out how to get that limit to be 1. So let's do another example. If I have the limit as x approaches 1, 1 is a real troublemaker. No, I think it's just easier. 2x minus 2 over x squared minus 1. So if I look at this, and I've got x approaches 1, so I've got 2 minus 2 over 1 minus 1. Is this the one we started with? I can't remember. Let's see here. 2x minus 2 over x squared minus 1. Yeah, that's the same one. So here we went through and we showed that the limit should be 1. Okay, so we know it should be 1. But we also said that this looks like 0 over 0. Oops, 0 over 8. Which means we can use L'Hopital's. I'll just do L'H shorthand. So then L'Hopital's rule says that, well, that's the same as the limit as x approaches 1 of the derivative of the top, which is just 2, over the derivative of the bottom, which is 2x. Which is, we can cancel these 2's. So we get 1 over x. So that's the limit as x approaches 1 of 1 over x, which is 1 over 1, which is 1. Same as earlier, but I would argue quite a bit quicker and easier. Once you've figured out that you've got 0 over 0, right, then you can just use L'Hopital's rule. Let's do an example where it's going to look like infinity over infinity. So if we've got another example here, the limit as x approaches infinity of the natural log of x over the third root of x. As x goes to infinity, the natural log of x, right, remember it goes, here's where remembering what the graphs all look like might be helpful. Natural log of x looks like this, so it's slowly going to infinity, and the third root is also going to infinity. So this, oh, that's the color I want. This looks like infinity. Clean that up. Infinity over infinity, which means I can use L'Hopital's rule. So I'll just say, use L'Hopital's. L'Hopital's rule says that I can rewrite this as the limit as x goes to infinity of 1 over x over x, the third root of x is the same as 1 over 3 times x to the negative 2 over 3, right? X to the 1 over 3 minus 1 is negative 2 over 3. And I can kind of rewrite this, right? I get a fraction over a fraction, essentially. So I can rewrite this as 1 over x over x to the negative 2 over 3 over 3, fraction over a fraction. Oh, whoops, what did I forget? My limit. My limit hangs tight here. So here I've got a fraction over a fraction, and so I've got the limit as x approaches infinity of 1 over x times 3 over x to the negative 2 over 3. Okay, the limit as x goes to infinity of, maybe what I'll do is I'll bring these x's up to the numerator. So I get 3 times x minus 1 times x to the negative 2 over 3. Which means I've got the limit as x goes to infinity. X goes to infinity of 3x to the negative 1 plus 2 over 3, because it's going to be positive now. Negative 1 plus 2 over 3 puts me at negative 1 over 3. So I get the limit as x goes to infinity of 3 to the times x to the negative 1 over 3, which is the same as the limit as x goes to infinity of 3 to the third root, or over the third root of x as x goes to infinity, right, I know this thing goes to infinity, and so 3 over infinity is going to go to 0. Okay. So a little bit more work, but again, I'm not sure how I would have dealt with this easily, or as easily as just taking the derivative of the top and the bottom and figuring out what the limit was of the derivatives. One thing, right, note, always check for the indeterminate form before using L'Hopital's rule. So always check for indeterminate form before applying L'Hopital's rule, right? Because now we've got this this fun trick for dealing with limits, but remember, it has to be an indeterminate form for it to guarantee to work. So let's do another example. If you've got the limit as x goes to pi, just a dead giveaway that it's going to be a trig function. So the limit as x goes to pi of sine x over 1 plus cos x, this would be the same as, I'm seeing 0. If I plug in pi into this function, I got 0 over 1 plus -1, 0 over 0. So I'm okay to use L'Hopital's rule. So L'Hopital's rule says that I can take the limit as x goes to pi, the derivative of sine x is cos x, the derivative of 1 is 0, the derivative of cos x is negative sine x. So now what I'm going to find is that if I plug in x equals pi here, I get -1 over 0. -1 over 0. Therefore, the limit does not exist. Okay. Here, L'Hopital's rule does not help. Right, so that can happen too. If we end up, maybe it's not so many exclamation marks, right? If we end up where the limit does not exist, right here we're dividing by 0. Even if after we've used L'Hopital's rule, what we could do, we could try maybe values around pi. So try limits around pi to see what happens, right? Things like x is 3.14, maybe 3.141, or x is 3.15, right? Approaching it from the other side, or 3.142. We could try those. We're not going to do that, but we could if we were desperate to find this limit, which in this case we're not, right? I'm just showing you that sometimes, even though we have this indeterminate form, we might end up where the limit does not exist, right? And so then we could branch out and look at some other limits. But how about another example? What if we want to find the limit as x goes to 0 of the natural log of x over x squared? This, to me, looks like -infinity. Again, really helpful if you remember what the natural log of x graph looks like here, right? As x goes to 0, I'm going to -infinity. So it looks like -infinity over 0 squared, so 0. this is not indeterminate form. Oops, too long of a word. Not indeterminate form. Can't use L'Hopital's. Rule. No. Like I said, there are going to be cases, if I just go back to L'Hopital's rule for a second here, right? L'Hopital's rule says that if we have some sort of limit like f of x over g of x, right? So if we have the limit of a fraction and the indeterminate form is 0 over 0 or infinity over infinity, right? This hinges on it being a fraction. There are going to be cases where we have to rewrite our function as a fraction, right? Kind of reword g of x or f of x to make it look like a fraction. Then we can apply L'Hopital's rule. So sometimes there's a little bit of work involved there, as in the next example. If we take the limit as x goes to 0 of x squared times the natural log of x, right? If I think about how this behaves, I'm going to have 0 times infinity, right? And I guess negative infinity, but it doesn't matter. Well, maybe it does. Let's not be sloppy. There. So here, this is indeterminate form. But need to rewrite, oops, 2. To look like either 0 over 0 or infinity over infinity. So I'd say the easiest target is to rewrite x squared in the denominator, right? I can just make the power negative and bring it down. And so what I'm going to do is I'm going to rewrite as f of x over g of x. So what I'm going to have is I'm going to have the limit as x goes to 0 of the natural log of x over x to the negative 2. X to the negative 2 is the same as, so the limit as x goes to 0, natural log of x over the 1 over x squared. That would put me back at x squared times the natural log of x. But here, what I'm seeing is I've got negative infinity over, and as x goes to 0 here, right, if I plug in x equals 0, I get 1 over 0, which is going to be infinity, right? So now, it's now in indeterminate form. We can use L'Hopital's. So now what I can do is this is the same as the limit as x goes to 0 of the derivative of the top, which is 1 over x, over the derivative of the bottom, which is negative 2x to the negative 3. I can simplify this thing, and so I get the limit as x goes to 0 of 1 over x, which is x to the negative 1. And then I've got x to the negative 3. So this I can rewrite as x to the negative 1 and times I can bring this x to the -3 up to the top times x to the -3. I'm dealing with this -2. I'm going to bring the 2 up top because it doesn't matter. And then it's all over 2. So what I get here is I get x to the -1 times x to the +3. -1 plus 3 puts me at 2. So I get the limit as x goes to 0 of -x² over 2. As x goes to 0, I get -0 over 2, which is just 0, which is the limit. Confusing with the period. Right. So the limit of this thing is 0. How we can think of it is that the x² won out, right? So the natural log of x is going to -infinity, x² is going to 0. It's basically a power struggle between 0 and -infinity, and it looks like x² won because it's going there faster. It's going to 0 faster. Okay, so that is actually the end of section 4.4. So that's all of L'Hopital's rule that you'll be expected to know. Right, so this last one that we used, where was it? This one, where we had to rewrite it. That's a little sneaky, right? But as long as you remember, okay, I need it in the form of 0 over 0 or infinity over infinity, then you can rewrite it as a fraction, right? Just using some little tricks maybe. And then hopefully you'll get it in an indeterminate form, and then you can just use L'Hopital's rule. I'm going to check for questions here. I see none. Okay. So the last section of the course, I'm as excited as you are, don't worry. 4.7, and it's a really fun section. So 4.7 is optimization problems. Optimization, how did I spell that wrong? Optimization problems. We've already hinted at optimization. Optimization is a huge field in mathematics. It can be applied to basically any other science as well, economics, biology, chemistry, any field that you're going into will have some sort of optimization problems in it. We're just going to look at some basics, right? But the ideas stay the same. They do involve derivatives. And so optimization is a major field of mathematics. So it is a major field of mathematics. And there's actually quite a large department up at UBCO if you're transferring up there. Heinz Bauschke and Sean Wang, they do a lot of optimization work, so pretty cool. Things like if you want to minimize cost or maximize benefit, right? Benefit in general, usually profit, right? But it can be anything. Okay. So what we want to do is because what we've learned, right? Optimization is usually a maximum or minimum, right? And so what we need is some function that models the cost or the benefit, and then we can find the maximum or the minimum of those functions. So we want we want a function that models cost or benefit, depending on which one we're working on, cost or benefit in terms of one variable. In terms of one variable. So what we're going to do, right, is usually we'll have more than one variable, but we're going to be given some constraints that we can incorporate, and we can rewrite this whole, the function that we're interested in terms of one variable. So for all our problems, we're going to be able to boil it down to one variable. Then we'll use the first or second derivative test, Usually the first will suffice, or the closed interval method. The closed interval method, remember, is when you find the critical numbers and then you evaluate the function at the critical numbers, but also at the endpoints. And then whichever one you're looking for, the maximum or the minimum value, is going to be at one of those points. And so often for these problems, we're going to be able to use the closed interval method. So it's good to kind of have a refresher on that. So we'll use the first or second derivative test or the closed interval method to find the best solution. Okay. So, like I said, typically our problems involve more than one variable, right? But what we'll have to do is we'll have to rewrite it in terms of just one variable. So typically our problems involve several variables. But additional information in the form of constraints, right, and you'll see what I mean by that, are going to allow us to reduce the number of variables. So, but additional information in the form of constraints will allow us to reduce the number of variables, Constraints are criteria that our solution must satisfy. Constraints are criteria that our solution must satisfy. Right. So kind of a common one that we'll start with is if we have some sort of fencing. So if we've got, this is kind of the most basic problem, you've got a wall here and then you've got fencing, you want to fence this area. So this is the problem that we're about to do, but just as a quick preview, right? But you've only got so much fencing that you can use, but you want to maximize this area, right? And so what we want to do is we want to take into account that, well, I can't have a negative width, for example, right? So the width has to be positive, but also, right, I have to maximize the amount of fencing that I have. So that's just one of the main types of examples. So here we go. Example. You have 800 feet of fencing. Like I said, this is the most basic type of fencing to build an enclosed yard. To build an enclosed yard off of one wall of a building. Off of one wall of a building. You don't have to build it off of one wall, but this is just to be able to have a bigger area, right, for 800 feet. So if you have a wall, then that's probably where you would build your fence. The fence will form 3 sides of the rectangular yard. Will form 3 sides of the rectangular yard. Rectangular yard. Find the dimensions. Find the dimensions for a yard with maximum area. For a yard with maximum area. Maximum area. So here, first thing I'm going to latch on to is figure out which thing I want to maximize. So the quantity to be maximized, is the area. So like I said, let's draw this thing out. I would say for a lot of these optimization problems, the hardest part is figuring out what you've been given, what your constraints are, what you have to maximize, and then being able to draw it out and put it into some sort of function, right? And so here we've got this wall. That's your wall. Keep going a little bit like that. And then what we're going to do is we're going to build a fence with some width, some length, and the same width, right? It's rectangular. So here it's quite easy to see that the area in here, right? The area we know is the width times the length. What we also said was that our constraints were that we only have 800 feet total, right? So the width plus the length plus the width can't go over 800 feet. So we have 800 feet total. So what we're saying is that 2W plus L ideally equals 800, but it has to be less than or equal to 800. But I'm going to maximize this whole thing. So I've got area in terms of W and L, right? What I'm going to do is I'm going to use this function to replace one of these variables. To make it easier for myself, I'm going to solve for L, right? Solving for W would work too, but it's just going to be a little bit nastier to deal with. And so here, area is in terms of W and L, but we can use the constraint that 2W plus L has to equal 800 to rewrite area in terms of only W. Oops, combine it. because what we can do is we can say, okay, well, 2W plus L has to equal 800. So L must be 800 minus 2W. So now our function to maximize, is A of W, which is, we've been writing it as the width times the length. So W times 800 minus 2W, right? Just showing that this one in here, actually, this one in here, I can expand this out. So I have A of W, A is a function of W now, so I get 800W minus 2W squared. So some other conditions, right? If I go back and I just kind of logically look at this yard, right? W has to be greater than 0, of course, otherwise there's no area here. So it has to be positive, but it can't be more than 800, right? I technically, I could use all my 800 feet and extend it this way. My area would be 0, but that is an option, right? It's not a good option, but it is an option. And so here, we know W must be greater than 0, and W must be less than 800. Making this, right, a closed interval from 0 to 800. So if we have a closed interval, the easiest thing I would say is to use the closed interval method. So since we have a closed interval, the closed interval method might be the easiest. Which is where we find the critical values or the critical numbers, and then evaluate f of x at endpoints and the critical numbers, and then select the maximum or the minimum depending on what you're doing for that problem. Right, so that's the closed interval method. And so let's try it here. We need to find the critical numbers. Remember that A of W was 800W minus 2W squared. 800W minus 2W squared. So the first option is, the first derivative is 800 minus 4W. Type 1 critical number is where this thing equals 0. A type 2 critical number is where this thing doesn't exist. There are no fractions, no square roots. There's no illegal math happening here. So the type 1 critical number is where the derivative is equal to 0. So if we have 0 equals 800 minus 4W, I can have 4W is at 800. So W must be 200. That's our one and only critical number. or type 2 critical numbers where the derivative does not exist, which is not applicable in this case. Okay. So we've got our critical numbers at w equals 200, and then our endpoints, right, we're at 0 and 800. And so what we do is we plug in w equals 200 and endpoints w equals 0 and w equals 800 into A of w to see which w maximizes A of w. Okay. So I've got A of 0 just starting from, the smallest, working our way through. A of 0 is 800 times 0 minus 2 times 0 squared, which is 0, right? Which makes sense if we're just doing a fence from here, and then we've used all our 800 there, the area is 0, right? So that makes sense. If we do the area, if the width is 200, then we get 800 times 200 minus 2 times 200 squared, which is going to be 80,000. I guess I can put this on the same page here, but now I'm going to be on the next page. A of 800, right? The other endpoint is at 800 times 800 minus 2 times 800 squared, which is negative 640,000, which is a bad area if you're trying to maximize this thing. Right. Oh, whoops. What was my mistake here? When I drew out my little sketch for A of 0, w equals 0 would look like this, right? The length would have to be 800. W equals 800 looks like this, so the length must be 0. Right? That was my little flub. Mm-hmm. This tells me that this is my max area. Right? I just look at what the area is at each of these points, and the maximum here is 80,000. So therefore, put it on its own. Therefore, the maximized area is 80,000 square feet. And just to kind of finish this problem, I'll show you how to do this problem with the first derivative test as well. But so we had to find the dimensions. So when W is 200, right, what we said earlier was that we found the length. The length is 800 minus 2W. So the length must be 800 minus 2 times 200. So the width, or sorry, the length. And the length is 800 minus 2W, which is 800 minus 400, which is 400. So the dimensions must be 200 by 400. Okay. That's the whole thing, right? That would be the end of this problem. Or we can use option number 2 to solve this problem. All right, we've got problems. We've got options. Is the first derivative test. Which I think we might be more familiar with, but I just like that we only have to find the critical numbers and then evaluate at the endpoints. If we have a closed interval, then that's a good go-to. So the first derivative test is when we have to find the critical numbers and then find the intervals of increase and decrease, and then identify maximum and minimum values. So we already found our critical numbers, and so A prime of W is 800 minus 4W, right? Skipping ahead a little bit. Our type 1 critical number, blah, 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 is when 0 equals 800 minus 4W. So that's when W is 200. We already determined that. And we already said that type 2 critical numbers are not applicable. So what do we do? To use the first derivative test, well, I've got a number line here. I know I can't be less than 0 and I can't be more than 800. Put 200 on here somewhere. Same thing as I just did in the review, right? The derivative of A is 800 minus 4W. If I just pick a point here, let's use maybe 100, and let's use, I don't know, 300, just to pick some values. Well, then I get 800 minus, and this is a case where it's actually going to be easier to just plug in the numbers, minus 400. That's a positive value. On this side, it's going to be 800 minus 4 times 300, which is going to be a negative number, right? So A of W itself is going to be increasing between 0 and 200, and then decreasing between 2 and 800. All right, and so here, this is as we vary the width of this thing. So here, the area is continuously, it's increasing, reaching a maximum at 200, and then the area is actually decreasing as we go through here. So this puts it 200 as a local max. Okay. So what we can say here is that the best width is at W equals 200, right? Because judging by this, I don't really have to evaluate the endpoints because I know I'm increasing from 0 to 200, and then I'm decreasing from 200 to 800. So using the first derivative test, I actually don't need to evaluate the endpoints because I can tell how it's behaving, right? So here I see that 200 is a local maximum. And so I can just use W as 200 as my maximized W. So again, then we can say that 2W plus 2L is 800. So 2 times 200, same thing as we did before, just kind of reiterating here. So L must be 400. And again, we're going to land at the areas L times W, or W times L if you prefer. 400 times 200, 80,000 square feet. Nice. So that's the end of that example. I'm going to check for questions here. Hey guys. No questions? Okay. Then let's do another example. Let's see if I have this one. Yeah, sure. Actually, maybe what I'll do is I'll use this other one and then use the one I was just about to do for reviewing it. How about that? So example, if we're on a lake, so here we've got this body of water here, and I want to get from point A to point B. Okay. I have two options, so I want to get from A to B in the shortest time possible. So I want to minimize the time in the shortest time possible. Okay. This tells me that I want to minimize time. Okay. Here are my options though. You can row, right? So here I am on the shoreline and I want to get to point B. Looking at this, right, I would just go straight across here, but this means I would have to row, and maybe if I'm faster at running, I could do another option is just run around the lake, right, and figure out what that would look like. So you can row 6 kilometers per hour, but you can run 8 kilometers per hour. Okay. Here are some dimensions that might be helpful. So from A to B horizontally is 3 kilometers, and from A to B vertically is 8 kilometers. Okay. So I've got kind of two extremes here, right? I could row across here and then run down here, or I can run across here and then row down here. Neither of those are going to be very good options. In fact, I think what might be fastest is if I row to some point here and then run the rest of the way. But we're going to explore all these options. So what we're going to do is we need to identify some variables that we can work with. So what we've got here is if we've got kind of right, so that distance is 8 kilometers. And if we put a hypothetical stopping point here, just to explore that option of rowing for a little bit to cut down the amount of time that I have to run, but also making use of the fact that I'm a faster runner, right? And so here I'm going from here to here, some distance, x, right? Cutting down the distance of 8 kilometers, right? 8 minus x is what I have to run then. So here, I'm going to row here, and then I'm going to run here. Okay. Pretend that this is a right angle. It's not, but whatever. Okay. So how far south on the opposite shore should you land the boat? Should you land the boat? Okay. So what we're saying is, okay, well, how far this way should we land, and then to max or to minimize the time, right? And so we want to find x that minimizes the time. So what we want to do is we want to find x to minimize the time. Now, what's a little bit tricky here is, okay, we've got speeds and we want to talk about time. And so, but we've also got distances. So we've got a couple of things going on here, but we have to remember the relationship that distance is the speed times the time. So time, right, that's the thing I'm interested in. Solving for time here, I get time must be distance divided by speed. Okay. So that's going to be important to keep in mind, right? We've got these distances that I'm going, so here I'm rowing probably, and here, well, no, I have to be rowing here, and then here I have to be running, right? And so the time, the total time is going to be broken up into the time spent rowing and the time spent running. So the total time is the time rowing plus the time running. Okay. If we break these up into two parts, right, and I'll clean this plus up because it's important, there. We can focus on what the rowing looks like. The rowing has a speed of 6. We'll ditch units for a little bit here. And it's going to look like we've got this right angle here. Here I am at A. This distance is x. If I call this d the distance, then I can just use the Pythagorean theorem because this I know is 3. And so I get d squared is 3 squared plus x squared. So d must be the square root of 9 plus x squared. Okay. The time spent rowing, so this is the distance that I'm rowing, but remembering that time is distance over the speed, well, I've got the speed here. So the time rowing is d over the speed, which is the root of 9 plus x squared over 6. This goes here. Right? We do the same thing for the running. In fact, it's going to be a little bit easier. So the time running, or actually let's focus on just the same setup. Running, our speed is 8, and the distance running is 8 minus x, whatever x is, right? And we want to figure out where should we stop rowing, right? Where should we be aiming for to minimize the time? So the distance that we're running is 8 minus x. So then the time running is the distance over the speed, which in this case is 8 minus x over 8, which, oops, 8 turns to 0. Oopsies. 8. This is the time spent running, so if I kind of pull that up there. Right, so now my total time, the time spent rowing is in terms of x, the time spent running is in terms of x, so now I've got time as a function of x. So the total time is now a function of x, right? So we can write t of x is the time spent rowing, so the root of 9 plus x squared over 6, root of 9 plus x squared over 6, plus 8 minus x over 8. To find the derivative of this thing, I'm going to split the 8 minus x over 8 and maybe rewrite this so it's a little bit nicer to take the derivative of. So I get 1 over 6 times the root of 9 plus x squared, oops, plus 8 over 8 minus x over 8, right? Just breaking this thing up. 8 minus x over 8, we can rewrite as 8 over 8 minus x over 8. So this becomes 1 over 6 times the root of 9 plus x squared plus 1 minus x, or I'll put the 1 over 8 in front because it'll make it easier to see the derivative. 1 over 8 times x. This is just the function, right, t of x that we want to minimize, right? And so again, I want to find the minimum value of this thing, which means I've got a couple of options, right? I can use the first derivative test, I can use the second derivative test, but probably best to use the first derivative if we can, or we can use the closed interval method. And so if we have a closed interval, so what we're going to do is we're going to find the critical numbers and use the first or second derivative test or the closed interval method. Or the closed interval method to minimize, oops, to minimize t of x. Notice that x has to be between 0 and 8, right? The whole distance here that it could be, if we go back to our diagram here, the whole distance that this could be is 8. And so the longest that x can be is 8, and the shortest that x can be is 0. So we've got x has to be between 0 and 1, or 0 and 8, sorry. And so here, if x is 0, that would be if we row straight east. And if x is 8, that means we row the whole distance. Right. So our critical numbers, right, and we see here that finding the first derivative is going to be a little bit of work. It is sort of just, well, it's not a quotient rule or anything nasty like that, but our critical numbers, the type 1 critical numbers is when t prime of x equals 0. And so here, t prime of x is going to be, now I need my t of x So I'm just going to copy it here so I can see it. Copy. And I'm going to paste it here just so I have my t of x. So t prime of x is going to be 1 over 6 times, and then I've got the square root here, so I've got times 1/2 times 9 plus x squared to the negative 1/2, but then I need the chain rule, so times the derivative of the inside, which is 2x. Now I'm done with that first term, and plus the derivative of 1 goes to 0, and then minus 1 over 8x. The derivative of that is just negative 1 over 8. So now I've got, well, I've got a couple of options. I see I've got a 2 and a 2 here, so I can cancel those, not have to deal with those. And I get, so I can clean this up a little bit. I can write this as x over 6 times the root of 9 plus x squared, right? Because I've got the negative 1/2 as the power. So the negative bumps it down to the bottom, and the 1/2 makes it a square root. And so minus 1 over 8. Okay. If I force this to equal 0, right? So find t prime of x equal to 0. So I get 0 is x over the 6 times 9, the root of 9 plus x squared, minus 1 over 8. Solving for x, I can bring this negative 1 over 8 over to the left-hand side, so I get 1 over 8 is x times 6 root 9 plus x squared. And now it's just a matter of algebra, right? I can bring 6 times the root of 9 plus x squared over to the left-hand side, bring the 8 over to the right-hand side, and so I get 6 root 9 plus x squared is 8x. One thing that I'm going to do, and there's a couple of different options that you could use, but one thing that I'm going to do to get rid of the square root is I'm going to square the whole thing. It might be easier to deal with. And so what I'm going to do is I'm going to have 6 times the root of 9 plus x squared squared. And what I do to one side, I have to do to both sides. So then what I get is I get 6 squared, which is 36, times 9 plus x squared is 64x squared. Okay. 36 times 9, I've got 324 here, plus 36x squared is 64x squared. 64x squared minus 36x squared, I've got 324 must be 28x squared. X squared then must be 81 over 7. One thing to remember, right, is that once we take the square root, so x is either the positive square root of 81 over 7 or the negative square root of 81 over 7. This is not a solution. Not a solution, since x has to be between 0 and 8, right? So we've eliminated that as an option. So the one that we're focusing on is the positive root of 81 over 7. We just want to make sure that it is between 0 and 8. And so we've got x is roughly equal to, and let me just do it here, 81 over 7, and then I take the square root of that. I get roughly 3.4016800257. So x is roughly 3.4 kilometers. So that's how far down I would need to go, right? And so for one of my critical numbers. So this is either a maximum or a minimum, presumably a minimum, but we have to make sure, right? And so since we are working on a closed interval, we can use the closed interval method. We can use the closed interval method. So if we've got, right, so what we have to do is we have to evaluate the total time at critical number and endpoints. Remember that t of x is 1/6 times the root of 9 plus x squared plus 1 minus 1/8x. It's important that you use the original function, not the derivative, right? And so what we've got is if x equals 0, let me just move this over here a bit. If x equals 0, then what I'm doing from A to B looks like this, right? So if x equals 0, then I'm rowing no distance across, right? I'm just rowing straight across and then I'm running. So t of 0 is 1/6 times 9 plus 0 squared plus 1 minus 1/8 times 0, putting me at 3/6, oops, 3/6 plus 1, which is 1.5 hours, since our speed was kilometers per hour, so our time must be in hours. So that's our first option. Probably not our best option, but let's have a look at the other endpoint. So the other endpoint was if we go just straight across to B, right? And so x equals 8. T of 8, again, is 1/6 times the root of 9 plus 8 squared plus 1 minus 1/8 times 8. This puts me at, once I solve it, 1.42 hours. That's less time than 1.5 hours. So now what I'm going to do is I'm going to evaluate the endpoint, or the critical number, sorry, which looks like, so if I'm going from A to B here, what we would do is we would go from here and then down, and then this distance we decided was 3.4 kilometers. So x is 3.4, so t of 3.4 is 1/6 times the root of 9 plus 3.4 squared plus 1 minus 1/8 times 3.4, which if we calculate it, 1.33 hours. Right. This is the minimized time, right? Because we've got 1.5, 1.42, and then 1.33 is the lowest. And so we would row to a point 3.4 kilometers south on the opposite shore, then run the rest of the way. Nice. Haha, saved by the bell. That's the whole problem. So those are some different optimization problems. There's some other ones, but that's the whole idea. So you've got a couple of options, right? The first derivative test, the second derivative test. But all in all, we just use the tools that we've been working on. Are there any questions? No? All right. If there are no questions, then I will quote unquote see you guys on Thursday. All right, so make sure you get your WebAssign. Oh, thanks, Jaden. Make sure you get that bonus assignment done on WebAssign, and we'll be all prepared for test 4. Cool. See you guys later. Good.